First, we are starting with important terminologies related to space science. And right, basic terminologies: launch vehicles, rockets, payloads, guidance system, propulsion system, and staged launch system. First, I will start with the launch vehicle. See this picture here. This is the GSLV Mark II. If I show you this picture and ask, what is this? What will be your simple answer? Rocket. Yes, we generally call it as a rocket, but technically this should be called as a launch vehicle. So why we should not call the entire system as a rocket is, you take a car. What gives power to the car? The engine gives power to the car. So engine is something that drives the car, but other than the engine, you have a lot of other components. You have fuel system, you have a glove box, seating capacity. The entire device is called as car, but the one that delivers power is called as engine. Very similar to that. The entire assembly is called as a launch vehicle, but the engine portion is called as a rocket. The rocket is one that delivers the power, and the entire assembly is called as launch vehicle. Coming to the next one. Where do we place the luggage here? Is it at the bottom or at top? The luggage that has to be sent, that will be kept at the top. Yes, that will be kept at the top. The luggage that you keep here, this should be called as the payload. You can write the definition later. First, you observe the entire assembly is called as launch vehicle, and the engine component is called as rocket, and the luggage is called as payload. Payload can be anything. Either you can send a satellite, or you can send humans. Astronauts can be sent, nuclear weapon or spacecrafts. Anything can be sent as a payload. So launch vehicle, rocket, and then payload. First, you can write a simple definition for this one. Rocket powered vehicle that can carry something beyond the Earth's surface. Noted this? Yes. The next one, rocket. So how do we define a rocket? You take a Diwali rocket, for example. You're igniting it. It is producing gas. It is getting propelled. Correct? The same definition here. It's a vehicle that obtains thrust by expulsion of gases. Simple definition. Followed by that, we'll learn the science behind it. Noted. And if you have seen a rocket engine, usually it will have a broad base and then a narrow top, what we call as the throat portion of the rocket. Any idea why the rocket is wider at the bottom and narrow at the top? We call it as a bell-shaped nozzle. Looks like this, almost like a bell. So why is that the top area is smaller and the bottom area is wider? Random guesses. Okay, we're going to learn about additional concept here from NCERT. We're going to define pressure. Any idea what is the formula for pressure? Pressure is defined as force by area. So I'm going to rewrite it. I'm going to say pressure equals to thrust by area. So instead of force, I've replaced it with the term thrust. What is the difference between force and a thrust? If you have a surface, and if the force is going to act perpendicular to the surface, then that's called as thrust. When you define something related to car, you don't use the term thrust because the cars are moving parallel to the roads. But when you talk about rockets, they're moving perpendicular. We can use the term thrust. From here, whatever is written in the numerator, I can say it is directly proportional, correct? Whatever is written in the denominator, those are inversely proportional. I'm writing pressure is directly proportional to thrust and pressure is inversely proportional to area of contact. Two important things. Pressure is directly proportional to thrust and pressure is inversely proportional to area of contact. Any day-to-day example, when we say inversely proportional, when one increases, the other should decrease. That is, when area increases, the pressure should reduce. When area reduces, the pressure should increase. Can someone tell any day-to-day example for us? Increasing the area for reducing the pressure, or reducing the area for increasing the pressure. Think and tell me. No? Where do we, yes? Pin, exactly. Safety pins or nails. You take nail, one end is broader, the other one is sharp. The sharp portion will be kept on the wall so that it can easily pierce inside. You're reducing the area to increase the pressure. Good. Any other example? You are about to tell something. Pin is an example. Yes. Whenever you get a water hose in, yes. Yeah, rubber band, that's an example. And then whenever you get a water hose, what is the first thing that you try to do? You try to close it, correct? And when you are closing it, you are reducing the area. When you reduce the area, what happens to the water pressure? It increases. That's an example. Then you take the shoulder bags that you're wearing. If you wear it with, if you wear it with one strap on one side, what happens? You feel more pressure. That's because area reduces, pressure increases. But if you wear it with two sides and a broader strap, what happens? Area increases, pressure reduces. You take trucks, for example. When the load is higher, they add more and more tires, correct? When they add more tires, what happens to the area of contact? Increases. Imagine 6 tires and then imagine 10 or 20 tires. Area increases and the pressure will reduce here. So those are the common examples. Very similar to that. You're reducing the area to increase the pressure, or you're increasing the area to reduce the pressure. A very familiar question in your SSC and other public service exams. Nails. How is it possible that people walk on the nail chappals or they lay down on the nail bed? Because area increases and the pressure reduces. Exactly. In the same concept here, we are putting a throat portion for the rocket. Area reduces. What will happen to the pressure? Pressure increases. For the given amount of fuel that you're burning, the pressure will drastically increase here. That's the concept here. Clear? If you have noted this, we can go to the next one. We have a globe. For online participants, if you have any doubts, don't wait till end of the class. We have a screen here. I would prefer to solve it then and there. I can unmute you at end of the meeting. That's different. But if possible, please post your messages instantly so that I can clarify. Yes. Back here. So far, you have learnt about two terminologies, launch vehicles and rocket. Coming to the next one, payload. That is the entity that's being carried will be called as payload. If you're taking a flight, you are the payload for a flight because the purpose is carrying you, correct? That's a payload. Noted this. Yes. Coming to the next one. Next is guidance system. So generally at the tip or top of the launch vehicle, we keep the payload. Keep this in mind. Yes. Coming to the next one, we are going to talk about guidance system. Have you seen the launch of PSLV or GSLV at least once, at least over the televisions? Yes, whenever they send it, it starts straight, but over time it will bend. Have you noticed? Yes. In which direction? To your right or to your left? Can you recollect from your memory? To your right, which means when we are sending something from the earth, or when we are launching something from the earth, we always tend to tilt it towards northeastern portion. We tilt it towards northeast. Before we learn why it is tilted towards the northeast, my question is how it is tilted. Because when you're driving a car, the car is in contact with the road, correct? So you can put, turn your steering wheel so that it turns. But right now, the launch vehicle is suspended in the air. When the launch vehicle is suspended in the air, how do you turn it? That's a question. What? Yes. From the boosters, okay. How do we turn using the boosters? Partially right, using the boosters. By controlling the fuel burns, and very important, what we call as counter steering. That is, have you heard about the term called as gimbals? Gimbal, that is the camera have gimbals, no? You have DJI, Osmo and all these. Yes, it's for stabilizing, very similar to that. We have gimbaled engines. That is, the bottom of the nozzle, it is attached with actuators and hydraulics. You can turn it. So since you can turn it, when the launch vehicle is moving, if you're going to tilt the gimbal towards southwest, it will tilt towards northeast. By adjusting the fuel combustion and also by changing the direction of the gimbal, we would be able to change the direction of the launch vehicle also, even after the launch. Clear? You can write in simple terms. We generally used gimbaled engines. Gimbaled engines to guide the launch vehicles after launch. To guide the launch vehicles after launching. Noted? Yes. Next question is, why do we tilt it always towards northeast? Why not towards northwest or any other direction? Why is it always in this direction? Very good. Because of the rotation of the earth. But my doubt here is the earth is rotating. The launch vehicle, is it attached with the earth or is it detached from the earth? It is detached from the earth. So how come the rotation of the earth is going to influence the movement of the launch vehicle? That's a question. Like you said, I was expecting this answer, which is very good. Moving from west to east. The earth is rotating from west to east. But in this case, the launch vehicle is detached from the earth. Then how is it the reason? Yes? Okay, because of the interaction with some link with the Coriolis effect, possible. But what is the Coriolis effect at the equator? 0. But even when you launch something from the equator, you will still tilt the launch vehicle. That's because in area, what is the average rotation of the earth? 1000 miles per hour or 1600 kilometers per hour. It depends on the location. That is, near the equator, it is 1650 kilometers per hour. And then when you go to the pole, it's spinning on the axis, which means it's 0 kilometers per hour. I'm writing here, the average velocity of the rotation of the earth is 1000 miles per hour, or we can say it is 1600 kilometers per hour. Now, the earth is rotating. Keep in mind, when the earth is rotating, the atmosphere is also rotating in a synchronized manner. That is, I'm going to represent atmosphere like this. What is the rate at which the atmosphere is rotating? The same 1600 kilometers per hour on an average. It will vary depending on the locations. Now, if I'm sending a launch vehicle like this, yes, I'm sending it like this, and then the wind is blowing in this direction, what will naturally happen to the launch vehicle? It will tilt like this. But if I send the launch vehicle in this direction, what will happen? What we call as the headwind and tailwind. Now, the launch vehicle will face headwind at a rate of 1600 kilometers per hour. That is, the launch vehicle will be moving, and in opposing direction, it will face a wind at a velocity of 1600 kilometers per hour. This will lead to multiple problems. First is stability. That is, the launch vehicle will wobble. And very important, have you heard about the aerodynamic stress? That is, the tip or the snout of the launch vehicle generally faces the highest temperature since it's piercing through the air, higher pressure and also higher temperature. Now, if you put it in the headwind, the aerodynamic stress will be even more higher. And then the third problem is you have to consume more fuel or you have to spend more fuel. If you put it in this direction, the launch vehicle is moving and atmosphere from the behind, it is pushing it 1600 km per hour, which is more easier. And that is why most of the times we tilt the launch vehicle towards northeastern direction, what we call as the gravity turn. You can write reasons for the gravity turn. We can write at least 3 reasons for the gravity turn. It's called as the gravity tilt or gravity turn. Reasons for the gravity turn. First reason you can write. First reason for the gravity turn. It reduces aerodynamic stress. Reduces aerodynamic stress. Second advantage is it reduces fuel expenditure. Third advantage is it increases stability. Increases stability of the launch vehicle. So these are the main reasons why we tilt it always towards northeast. Have you understood this? Yes. Coming to the next one. And have you noticed most of the launch stations will be on the eastern coast of the continent? That's because you're going to anyway tilt it in northeastern direction. And if there's a failure, what will happen? It falls into the ocean. You take Cape Canaveral in Florida. Failure falls into ocean. French Guiana. Failure falls into the ocean. Sriharikota, failure falls into the ocean. That's the reason most of them are here. But there are few exceptions. If you take Russia, Russia would have placed launch station here. That's because even if there is a failure, it is going to fall somewhere in the cold desert region where they don't have or they have very lesser human habitation. So most of the launch stations are in eastern coast of the continent. Clear? Yes. Coming to the next one, propulsion system. Next topic is propulsion system. Under propulsion system, a simple statement. Air is required for combustion, yes or no? Air or oxygen is required for combustion, yes, no? Yes, without oxygen or without air, you cannot burn anything. My question is, if the launch vehicle is moving here, that is within the atmosphere, the yellow color highlighted section that you see here, these are the regions with air. Now, when the launch vehicle is moving within the atmosphere, no problem. It has air supply, it can burn the fuel. Question is, what happens when the launch vehicle moves outside the atmosphere? Let's say it's traveling to Mars or Moon or any other different space objects, and it's traveling in the vacuum. How do we burn the fuel? That's a question. How is it possible? How can we propel the launch? Random guesses. We have to provide oxygen. That's all. Generally, in the launch vehicles, there are 2 containers like this. One is for fuel. The other one is for oxidizer. When we say oxidizer, it's not exactly oxygen. There are materials like nitrogen tetroxide, mixer oxides of nitrogen. They will provide oxygen. So once the launch vehicle goes outside, you have 2 compartments. You have fuel here and then you have oxidizer here. Then we use a simple valve mechanism. Valve will mix fuel and oxidizer. It burns and then it produces thrust. Is it clear? You can write the general propulsion system that we use is fuel plus oxidizer combo. When we say fuel plus oxidizer, we call it as hypergolic fuels. You write the term, then I will explain you what is meant by hypergolic. Okay. The term hypergolic means if you take an internal combustion engine, that is your car or a bike engine, it usually needs a spark plug, correct? That is, the fire ignite mixture. But here it's not the case. Do you see any engine pistons or anything? No, it's purely a chemical reaction. That is, fuel and oxidizer, if they come in contact with each other, they will instantly burn. You don't need any ignition mechanism. And that's the reason when they transport the fuel to the Shrierikot, generally it's transported through the highways in Chennai. First, for the fuel, they will have full security convoy. With full security, they will transport the fuel. And followed by that, next will be the oxidizer. But oxidizer and fuel, they're never close to each other. That is, 1 or 2 days before the launch, they will fill the fuel, but they won't fill the oxidizer. 24 hours to 48 hours before the launch, they will put the oxidizer in the other compartment, because placing them closer to each other is extremely dangerous. One molecule of fuel and one molecule of oxidizer comes in contact, they will instantly burn. You don't need any external ignition mechanism. So hypergolic basically means highly reactive fuels. It's a chemical reaction and the reactivity is higher. You can write hypergolic is otherwise called as highly reactive fuels. Hypergolic fuels or highly reactive fuels. There are solid fuels, there are liquid fuels, there are cryogenic fuels. We will discuss about it one by one. So far we have completed till propulsion system. The last one is staged launch system. So have you seen that the launch vehicle have multiple stages? Recently there was an article about the PSLV. So they would have written it as 4-staged launch vehicle. So you have stage 1, stage 2, stage 3, multiple stages. What is the reason for having multiple stages? Because you will detach the stages. That is, if you take the GSLV, for example, this is first stage, this is second stage, and this is third stage. What we have to keep in mind here is, how many engines will be there for a car? 1. But launch vehicles will have multiple engines. That's because, see this one. This particular one will have one engine here. Once the fuel is over, the compartment along with the engine will be detached. Then this is the second stage. When the fuel in the second stage is over, the compartment along with the engine will be disposed of. Like this, we will be disposing many engines. Usually the Indian launch vehicles have somewhere between 4 to 10 engines. But if you take Falcon 9 from SpaceX, all these have more than 45 engines. There are launch vehicles with 40 plus engines, or sometimes it goes up to 60 engines, depending on the configurations. Keep in mind, launch vehicles have multiple engines and multiple stages. What happens to the detached stage? That's the question here. You're detaching it in the space, correct? What will happen to all the detached components? We are detaching because we want to reduce the weight. Fuel is over and the compartment is empty. There is no point in carrying it, so you're expending it or you're disposing it. What happens to disposed stages or the detached stages? It can either orbit around the Earth, what we call a space debris. Sometimes it falls into the Earth. There are two possibilities. We are dividing the possibility as this is the Earth and this is the atmosphere. First, we're going to talk about endo-atmospheric detachment. That is, we are going to detach something within the atmosphere. Second one is exo-atmospheric detachment. That is, we are going to detach something outside the atmosphere. When you detach something within the atmosphere, what happens is it will fall down. Still under the influence of Earth, within the atmosphere, it starts falling from top part of the atmosphere towards bottom part of the atmosphere. Which part is thicker, bottom part or the top part? We take atmosphere, lower atmosphere and upper atmosphere. Compared to these two, which atmosphere will be thicker? Bottom part of the atmosphere or the lower atmosphere is thicker and top part of the atmosphere will be thinner. When you're detaching something, the debris is falling from thin part of the atmosphere towards thick part of the atmosphere. What will happen to density? Will it increase or reduce? Increases, because thinner to thicker. The density increases, temperature increases, and then it starts burning. Whatever you're detaching from the top part of the atmosphere, when it falls towards the bottom part, it starts burning. When it starts burning, there are possibilities. Either it will completely burn, or if something is left over, it will fall into the ocean. So I'm writing here, when endo-atmospheric detachment happens, first is a complete disintegration can happen. That is, completely it can burn if it is of lesser mass. Second possibility is it can fall into ocean. If at all anything is left over, it falls into ocean. But when you're detecting something outside the atmosphere, it starts floating around the Earth, what we call as space junk or space debris. So this is a simple principle. Within atmosphere, it will fall inside. Outside the atmosphere, it becomes space debris. Is it clear? What are the methods to reduce the space debris possibilities? One is preventive, other one is curative. When you say curative measures, you already have a lot of debris. No? There are multiple space agencies that are trying to clear the debris. That is using a net type of mechanism. You can just grab all the debris and then you can push it inside the atmosphere. That is one possibility. Other possibility is people are trying to burn it in that, in the space itself. There are multiple things that are curative in nature. We'll talk about it later. But the preventive mechanism is we can use reusable launch vehicles. When we say reusable launch vehicles, how it basically works is, see, let's say this has a particular, say 100% of fuel is here. If you take a normal launch vehicle, we will exhaust the 100% of the fuel and then we will detach it. It falls. This is usual. But in expendable launch vehicles, once say 70% of the fuel is over, you will detach it. And then slowly you will bring it back in this manner, what we call as the reverse firing rockets or retro rockets. So the same boosters or sometimes the core stage will be brought back and then it will land on the surface. You can refill it or refuel it and then you can reuse it. These are called as reusable launch vehicles. By this principle, we can divide the launch vehicles into two types. I'm writing here. Launch vehicles can be divided into two. One is called as expendable launch vehicles. The other one is called as reusable launch vehicles. Expendable and reusable. Expendable means it's one-time use, used only once. Reusable means you can repeatedly use it again and again. Is it clear? Can we go to the next one? Have you noted this? Right. Coming to the next one. We have completed till this. Do you have any doubts in these 6 terminologies? No. So next we are going to talk about satellite orbits. Put the title as satellite orbits. I understand for some of the batches online, the science has already been completed. We will arrive at a solution for this problem. For now, you just listen to the class. Yes. Next concept is we are starting with satellite orbits. Why we are learning about the classification of satellite orbit is, see, how do you imagine a satellite orbiting around the Earth? Usually, you may imagine something like this, correct? Or you may imagine something orbiting like this, because that's how most of the space agency logos looks like, correct? But have you ever imagined a satellite orbiting like this from top to bottom? Very rare. You wouldn't have seen in logos, but there are satellites that orbit like this also. It orbits like this, or maybe from top to bottom also. So we are going to learn the classification of satellite orbits based on orientation. When we say orientation, it is about the angle of tilt. That is the first classification. Second classification is based on altitude. That is, I can place a satellite here at a particular height, say a lesser height or a medium height, or maybe a much higher place. Why this is important is the coverage area will depend on the altitude. If I place it closer, coverage area will be lesser. If I keep it far away, what will happen? The coverage area will be wider. So we are going to learn the classification of satellite orbits based on two different things, that is First based on altitude, the other one is based on orientation. For now, you can write classification of satellite orbits based on altitude. Mind map is there in your academic book. For now, you can write classification of satellite orbits based on altitude. Tell you the reference page number. The terminologies that you have learned so far, it starts from page number 5 all the way till page number 8. The basic terminologies, the terminologies in academic book, it's from page number 5 to page number 8. Then classification of satellite orbit, it starts from page number 8 all the way till page number 11. 8 to 11. Page number 8 to page number 11. You understood? Yes. Now, classification of satellite orbits based on altitude. Three is given: low Earth orbit, medium Earth orbit, and high Earth orbit. Now, I will tell you an analogy or an example here. Let's take, we have a apartment building. Yes. And then the apartment has multiple stories: ground floor, first, second, third, fourth, fifth. Altogether, 5 floors are there. And then there is a car that's parked here. Now, the task given to you is, you cannot stand on the ground floor. You can choose first, second, third, or fifth floor, third, fourth, or fifth. And you have to take a high resolution picture of this car using your phone camera. Yes, high resolution picture of this using your phone camera. Which is your preferred floor here? First or fifth? If you go to the 5th floor, you will have a wider angle, but will you get a high resolution picture? No. If you want a high resolution picture, you have to be in the 1st floor. So for taking photographs, I would prefer to stay at the lowest altitude. Then I want to check if a shop that is located in the street is open or not. I want to check if it's open or closed. Then which is the preferred floor? Then 5th floor. Because if you go to the higher altitude, the tree cover and everything, you'll be above the tree covers and you'll be able to see to a farther distance, correct? Very similar to that. If you place a satellite here, we call it as the low Earth orbit satellite. It is more suitable for capturing photographs because it's closer to the surface of the Earth. Then if you take satellites placed near the 3rd floor, for example, we call it as medium Earth orbit satellites. I will tell you the uses later. And then if you place it in the 5th floor, we call it as higher orbit satellite, lower orbit, medium Earth orbit, and higher orbit. If I place it at the lowest orbit, I can capture very good photographs. But if I place it in the 5th floor, I have a wider viewing angle, which means whenever I need a wider coverage, telecommunication, television broadcast, radio broadcast, for all these purposes, I'll be placing at the highest altitude. So which will have a narrow coverage area? Low Earth orbit. Which will have a wider coverage area? High Earth orbit. But which will have a better picture clarity? Low Earth orbit. But which will have a, again, wider coverage area? High Earth orbit. Then in terms of signal strength, if you place it here, the signal strength will be higher. If you place it here, signal strength will be comparatively lesser. Is it clear? Okay, so we can start defining it one by one. First is low Earth orbit. Put the title as low Earth orbit. For low Earth orbit, if satellites are placed between 180 kilometer up to 2000 kilometer altitude. 180 up to 2000 kilometer. We are talking about the vertical altitude. 180 to 2000. Those are called as low Earth orbit satellites. Then general uses, you can write. Usually Earth observation satellites. Earth observation satellites are placed. When we say Earth observation satellites, example includes mapping satellites or surveillance satellites. All these are called as Earth observation satellites. Any satellite that's used for capturing photograph, you call it as Earth observation satellite. Noted this? Yes. Next is medium Earth orbit. How do we define medium Earth orbit? Is if the altitude is somewhere between 2000 kilometer up to 35,786 kilometer. 2000 to 35,786. Then we call it as MEO or medium Earth orbit satellite. Generally, satellites used for navigation systems. Have you heard about GPS, IRNSS? All these satellites will be generally placed in medium Earth orbit, 2000, 35,786. Then, high Earth orbit satellites. High Earth orbit satellite means any satellite that is placed above 35,786 kilometer will be called as high Earth orbit satellite or HEO. Above 35,786. Noted? Yes. Generally, what are the satellites placed in high Earth orbit? You can write communication satellites. When we say communication satellites, it includes television and radio broadcast, telecommunication satellites, weather monitoring satellites. All these are placed in HEO or high Earth orbit. TV broadcast, radio broadcast, telecommunication, and weather monitoring satellites, all these are placed above 35,786. Any other doubts to this? No? Yes? Yeah, the strength of the signal will be comparatively lesser for a high Earth orbit satellite. But if you take your mobile phone communication, yes, usually you send voice data, correct? For voice data, most of the communication happens through towers and ground networks. So you may think it uses satellite. No. Satellite phones are different, and the phones that we are using is different. From here to the nearest cell phone tower, that is wireless. Mostly from tower to tower communication, it will be wired communication. We'll be learning it in electronics and ICT portion, where we'll talk about circuit switching and packet switching and all the other concepts. Usually, the communication happens in wired medium, even for your cell phone communication. Yeah? But here, signal strength will be lesser. And that's why if you take a TV broadcast, yes, most of the times it's very difficult to stream a 4K or 8K video because the signal strength is comparatively lesser. You have full HD, that's all. You don't have quad HD or anything in the streaming services, at least in India, because the strength of the signal will be comparatively lesser. If at all they want a full HD streaming, first high Earth orbit for coverage, and then multiple satellites will be there in low Earth orbit for an enhanced coverage. So we cannot say that mapping satellites are located only in low Earth orbit. I'm giving a very generalized explanation now. Most of the mapping satellites are in low Earth orbit. Most of the navigation satellites are in medium Earth orbit, and most of the telecom satellites are in high Earth orbit. But there are many exceptions. You will learn it over time. Yes. So we have learned about the classification of higher satellites based on altitude. Do you have any doubts on this? Why particularly 35,786? You're given a particular range. No, that's because when you take a satellite and then if you place it at exactly 35,786 kilometer from the Earth, the rate at which the Earth is rotating, the rate at which the satellite is moving, both will be synchronized or it will be equal. So that's why we have the limit called as 35,786. Next, you can write classification based on orientation. classification based on orientation. The orientation, first you can write polar orbit satellites. First is polar orbit satellites. The polar orbit satellites. Let's take this as the Earth. The Earth, is it straight or is it tilted? Tilted by 23.5 degree, correct? I'm going to put it something like this. It is tilted by 23.5 degree, not exact representation, but for understanding purpose. Now, you know that there is something called as geographic north and geographic south. And then we have something called as magnetic north and magnetic south, correct? First, we will talk about geographic north and geographic south. Polar orbit satellite means it should orbit from pole to pole like this. But it can be a little bit tilted also. So first you can write polar orbit satellites orbit from pole to pole. Polar orbit satellites orbit from pole to pole. Next line you can write polar orbit satellites can have an inclination up to 15 degree with respect to poles. Polar orbit satellites can have an inclination up to 15 degree with respect to poles. That is, it can either orbit from pole to pole, or it can be something like this also. Take a look at this. This is not aligned with the poles, correct? But still, this is a polar orbit satellite. Take a look at this picture. Do you see the location of the poles? It's here. But do you see the location of the orbit? It is inclined. What I mean to say is, when we say polar orbit satellite, it doesn't mean it should pass above the poles. It can be a little bit tilted from the pole also. Is it clear? And one last line you can write, it's a type of low Earth orbit. Most of the polar orbit satellites, they're placed in low Earth orbit. It's a type of LEO. The type of LEO, or the low Earth orbit. It's a type of low Earth orbit. Yes. Coming to the next classification, sun synchronous polar orbit. Next is SSPO, or sun synchronous polar orbit. So what happens in sun synchronous polar orbit here is, right now we are in daytime and half of the Earth is in nighttime, correct? Why is that? Because only half of the Earth receives sunlight, the other half it will be on the other side. So in this case, I'm going to draw an imaginary line. The red color line that you see here, this is an imaginary line that separates the side that receives sunlight, the side that is away from the sunlight. So the side that receives the sunlight is yellow. The side that's away from the sunlight, it's in black. And if you see here, poles and this line are not aligning with each other because the Earth is tilted. Have you understood this? Yes. First, let's talk about polar orbit satellite. If a polar orbit satellite starts from pole to pole, observe this carefully. It's moving from pole to pole, and it is covering areas that have sunlight, and it's also covering areas that are not having sunlight. Have you understood this? Yes. I'm going to make a small alteration here. You take the blue color satellite here. This particular satellite is going to orbit like this. When it orbits like this, is it going anywhere towards the darker side? No, it is always covering portions that are illuminated by sunlight. This is synchronized with the sun. That's called as sun synchronous polar orbit satellite. So you can write, first line you can write for SSPO, it's a type of polar orbit. This is also polar orbit. It's a type of polar orbit. SSPO is a type of polar orbit. Next line you can write, the satellite covers the areas of the earth. The satellite covers areas of the earth that are illuminated by the sunlight. Satellite covers areas of the earth that are illuminated by the sunlight. The satellite covers areas of the earth that are illuminated by the sunlight. In simple words, this is the polar orbit satellite and this is the sun synchronous polar orbit satellite. Because certain experiments, it always requires constant sunlight. Best example, spy satellites. The advantage of sun synchronous polar orbit satellite is, let's take, there is one sun synchronous polar orbit satellite that's going to cross above Karol Bagh in 3 different times. 6 a.m., morning 6 a.m., then 12 noon, and 6 in the evening, for example, which means every single day of the year, it will cross at the same time. 6 in the morning, 12 in the noon, 6 in the evening. So I can have a year-long observation. What happens on a particular area in a particular time. So most of the spy satellites are sun synchronous polar orbit satellite. Is it clear? Now try reading this one. The satellite passes above a given point at same local mean time. This is one unique characteristic of sun synchronous polar orbit because you are aligning the satellite based on sunlight. Clear? So you can write, satellite passes over a given point at same local mean time. Satellite passes on a planet surface at same local mean time. Noted this? Yes. You learned about polar and sun synchronous polar. Coming to the next one, geosynchronous orbit, GSO, geosynchronous orbit. So to understand geosynchronous orbit, earlier it was called as sun synchronous. Right now it's called as geosynchronous. Geo means earth synchronous. How it basically works is, let's take this is the earth. See, geosynchronous and geostationary earth orbit. These two are closely linked and it's often confused. Pay more attention. Let's take this earth and we are putting an imaginary line here. I mean, the equator, which is tilted. Any doubt till this portion? No. What happens here is, what is the time taken by the earth to complete one rotation? Just one rotation. Not around the sun, on its own axis, like this. Time taken for one spin. 24 hours, correct? What we call as one day. Approximately 24 hours. To be more precise, 23 hours, 56 minutes and 4 seconds. Now, geosynchronous basically means the time taken by the earth to complete one rotation is 24 hours. The time taken by the satellite to complete one orbit is also same 24 hours. It is synchronized along with rotation of the earth. You call it as geosynchronous. Sun is not related here. The rotation depends on the earth, or the orbit depends on rotation of the earth. That's called as geosynchronous. Under geosynchronous, first line you can write time period of the satellite. Time period of the satellite for geosynchronous orbit. Time period of the satellite equals to rotational period of the earth. time period of the satellite equals to rotational period of the Earth, which again equals to 23 hours, 56 minutes, and 4 seconds. 23 hours, 56 minutes, and 4 seconds. Pooja ma'am are like high Earth orbit satellites. Yes, these are very similar to high Earth orbit satellites, geosynchronous. Time period of satellite equals to rotational period. Another important thing to note here is we have the equator here. Generally, geosynchronous orbit satellites, they're not placed above equator, they'll be tilted from the equator. So you can write inclination of GSO will be greater than 0 degree with respect to the equator. Why this is important is, let's say we have placed a satellite here. Is it on the equator or tilted from the equator? Tilted from the equator. Since it's tilted from the equator, what happens is, you see the orbit. You'll divide the orbit into two different portions. First, it covers northern hemisphere. Then it covers southern hemisphere, correct? When it covers northern hemisphere, it won't be able to provide coverage in southern part. When it covers the southern tip of the Earth, it won't be able to cover northern part, which means it cannot uniformly cover both northern and southern hemisphere. Let's take if I am the Earth, and this is the equator portion, for example. I'm not going to place it on the equator, but I'm going to tilt it from the equator. Now, first half of the rotation, is it covering the northern hemisphere or the southern hemisphere? Northern hemisphere. At some point, it's going to cross the equator, and then second half of the rotation covers southern hemisphere. Again, it crosses the equator. Again, it covers northern hemisphere. It keeps on covering different parts of the Earth at different points of time. And because of this, what will happen is, let's take, this is the equator, that is 0 degree. And if you spot all the areas that's covered by GSO, the coverage area will look like this. You can draw. It looks like an infinity loop or an H shape. That is, I'm going to place it here. It's going to cover multiple areas here and multiple areas here. But when you project it on the map, you're going to take the Mercator projection, you're going to put it in a single piece of paper. So this will be the coverage area of geosynchronous orbit satellite. This is the northern hemisphere and this is the southern hemisphere. You'll understand its uses a bit later. For now, you can copy this one. Very difficult to imagine this, I understand. But if you plot all the places covered by the satellite during one rotation, and then you put it on a 2D map, it will look like this. Noted. Very important point is this one. Inclination should be greater than 0 degree. Noted this? Okay. Can you go to the next one? Yes. Next is geostationary Earth orbit. What is the abbreviation we have written for geosynchronous here? GSO. Here you can write GEO. Geosynchronous is written as GSO. Geostationary Earth orbit is written as GEO. For GEO, first line you can write, it's a type of GSO. Very important, it's a type of GSO. The type of geosynchronous orbit. Do you remember? Polar orbit and sun synchronous polar orbit. For sun synchronous polar orbit, you have written it's a type of polar orbit. Very similar to that. GSO, and then one special case is GEO. GEO is a type of GSO. Clear? Next line you can write time period of the satellite. Time period of the satellite equals to rotational period of the Earth. Same concept you're repeating again. Time period of the satellite equals to rotational period of the Earth. Time period of the satellite equals to rotational period of the Earth, which equals to 23 hours, 56 minutes, and 4 seconds. But at the same point, we have written for GSO also, correct? Only difference is it's kept or it is placed above equator or on the plane of equator. You can write GEO is placed above the equator, or in other words, no inclination. GEO is placed above the equator. So what's the advantage of placing it above the equator? See the coverage, no? It can cover north and south at the same time. That is northern part and southern part at the same time. And it can cover a wider area also. We can write one geostationary Earth orbit satellite can approximately cover 1/3 of the Earth. Approximately cover 1/3 of the Earth. There's one advantage. And you can also write coverage area looks like this. If this is the 0 degree, approximately the coverage area looks like this. Covers equal amount of northern and southern hemisphere like a square patch, because it's uniformly placed above the equator. Understand the difference? One is tilted, other one is on the equator. This will have a coverage area that looks like infinity loop, and this will have a coverage area that looks like a square patch. Now try reading this one. This is geosynchronous, tilted. This is stationary, on the equator. Tilted from the equator, on the equator. Is it clear? The major advantage here is, if you take this, it's 0 degree, the Earth is tilted. Take this is the 0 degree. Look at this satellite. It is covering, say, South America and some part of North America. Now, these people will have access to it 24/7 because the Earth is taking 24 hours to complete one rotation, and the satellite is also taking 24 hours to complete one orbit. Anything that requires real-time communication, live broadcast, availability of telecoms, everything needs geostationary Earth orbit satellite. The reason we call it as geostationary Earth orbit is, let's say you have a powerful telescope and then you are looking at a particular satellite that is above you. Right now the time is 2 o'clock, 2 p.m. You see the telescope, you see the satellite is above you. Somewhere in the midnight, say 11 or 12 p.m., you're just checking if it is there. It will be there. Morning 6 a.m., it will be there. For you, it looks like it is stationary, but it is not stationary. You are spinning and the satellite is also orbiting. Both of them are synchronized, making it appear to be stationary. That's why it's called as geostationary Earth orbit. Is it clear? Can you go to the next one? The last one is geostationary transfer orbit. Next one is GTO, or geostationary transfer orbit. To understand the transfer orbit, I will tell you two examples. You try to answer which one is beneficial. This is Earth. And we plan to place a satellite somewhere at 37,000 kilometer. Clear? We plan to place it somewhere at 37,000 kilometer. First approach is we are planning to send a launch vehicle that reaches here. How much kilometer? 37,000 kilometer. Fuel expenditure and everything is higher. Second methodology is, please observe here carefully, we are sending a launch vehicle that puts a satellite somewhere here at 6,000 kilometer. What was the actual intended orbit? 37,000, but we have placed it at 6,000 kilometer. Now the satellites will have small motors, and these motors are powered by solar power because sunlight is available. Solar panels will convert it into electricity, the electricity will be used for driving the motor, which means it's more cost efficient, correct? Then the satellite approaches closer to Earth. What happened to gravity? Increases. Using the increased gravity, it reaches here. Again, we reach closer to Earth, use gravity, reach here. Again, we reach closer to Earth, and then we reach here. This is the second approach. Compared to the first approach that directly reaches 37,000 kilometer, and the second approach that uses successive gravity assistance from Earth, that's the second approach. Which one will take more time? Second one will take more time, yes. In which of the following the satellite has to travel longer distance? Second one, but which will save cost here? Second one, that's the smartest way to send a satellite. All these temporary orbits that you see here, those are called as transfer orbits, because you're putting it here, you're transferring it to next orbit. Again, you're transferring it to next orbit. Again, you're transferring or elevating it to a different orbit. So you can write GTO or geostationary transfer orbit, GTO, or temporary orbits, GTO or temporary orbits used by the satellites, GTO or temporary orbits used by the satellites before reaching the desired orbit. Before reaching the desired orbit. Temporary orbits used by the satellites before reaching the desired orbits. The next line you can write. Satellites use gravity assistance. Satellites use gravity assistance from the Earth. Satellites use gravity assistance from the Earth to save the fuel consumption. To save the fuel consumption. Satellites use the gravity assistance from the Earth to save fuel consumption. That's all. Take a look at this one. So you have all the temporary orbits here. 1, 2, 3, 4, multiple orbits. Take a look at this. Here. This is the Earth and this is orbit of the satellite. Take a look at the velocity given here. Whenever it approaches closer to the Earth, look at the velocity, it increases somewhere up to 5 or 10 kilometers per second. You see a lot of magenta lines here. All these are temporary orbits, otherwise called as transfer orbits. The reason I'm explaining about this is when we talk about launch vehicles, you take any launch vehicles across the world, the capacity of the launch vehicles are measured by how much payload they can carry to the low Earth orbit and how much payload they can carry to the geostationary transfer orbit. They will never mention it as GEO or GSO because all the space agencies send the satellites to GTO. From there, they elevate it. That's a concept here. Is it clear? Okay, so we have completed till satellite orbits. Do you have any doubt on the satellite orbits? Please wait on that. Excuse me. This will be the general structure for most of your modules. That is, if we start astrophysics, for example, all the basic concepts, at least for 1 or 1.5 hours, and then we'll go into the technological portion. If you find any difficulty in comprehending the topics, you let me know in advance. Clear? First, for ISRO, I'll give you a timeline. The reason for a timeline here is when you prepare your standard notes, you should know a general idea about how the space program progressed in India. Space program, nuclear program, for all these, you should have a general timeline. Any idea when ISRO was started? That's when ISRO was started. But the actual space program in India started much earlier, starting from 1962 itself. So you can start writing the timeline and you can find the same in page number 11 in your book. You can write the reference, page number 11 in your academic book. The first important timeline that you can remember, 1962. So 1962 is important because India established an organization called as INCOSPAR. INCOSPAR, or otherwise called as the Indian Space Research Organization. It's a precursor to ISRO. They started with INCOSPAR. Dr. Ramanathan and Dr. Vikram Sarabhai. They were the head of these. And Jawaharlal Nehru was the prime minister. He initiated this project. Then in 1963, very next year, India launched the first sounding rocket. Right? India launched the first sounding rocket. What's meant by a sounding rocket? A research rocket, which means it won't carry a satellite or any other instrument. It's only for testing the launch systems. Do you know where it was launched from? Tumba Equatorial Rocket Launch Station, which is located in a village called as Tumba, located in Trivandrum in Kerala. Interestingly, India's first launch pads, they're located in Trivandrum. And then the next important one is 1967. 1967, India sent the first. Yes. Yeah. So I meant to say why it was launched from Tumba. See here, you have geographic north and magnetic north. Very similar to that. We have the geographic equator, and then there is something called as magnetic equator. So this magnetic equator, you see here, it runs very closer to southern tip of India. This is the magnetic equator, which depends on magnetic activity of the Earth. When we send rockets or when we send launch vehicles, we also wanted to test the influence of magnetic field of the Earth. For that reason, we built multiple smaller launch stations near southern tip of India, which is in Trivandrum. That's the reason. Clear? So in simple words, it's to test the influence of magnetic field of the Earth, or it's to test the influence of magnetic equator on rocket launches. That's the reason we chose southern tip. Have you understood this? Yes. Coming to the next one, 1967, India launched the first indigenous sounding rocket. India launched its first indigenous sounding rocket. By the way, the name of the rocket is RH-75. Till date, all the sounding rockets of India, they have the prefix RH. RH stands for Rohini. RH-75 basically means Rohini. 75 centimeters is the diameter of the rocket. RH-75, India's first indigenous sounding rocket. Noted this. Next important timeline, 1969. ISRO was established in 1969, August 15, 1969, on the Independence Day. They announced the establishment of Indian Space Research Organization. Then 1972 is important because Department of Space, exclusive department for space programs were established in 1972. So till this, ISRO was actually functioning under Department of Atomic Energy. Interestingly, in course part or ISRO, it was operating under Department of Atomic Energy till 1972. Note of this. Can someone tell which was the first satellite launched from India? First satellite launched from India. Any guesses? You have learned Aryabhatta is the first satellite of India, correct? Built by India is different. Launched by India is different. So first you can write 1975. Aryabhatta was the first satellite built by India, but it was launched by former Soviet Republic, USSR. So the first satellite of India, without any doubt, it is Aryabhatta, but launched by Soviet Republic. Then 1980, there was a satellite called Rohini, which was built. It was also launched by India. Or in very simple terms, The first satellite built by India was Aryabhatta, but the first satellite launched from Indian soil, it is Rohini. Is it clear? So this is sufficient, and more timeline is given in your academic book. You can go through it later. Whenever you see the term Aryabhatta or Bhaskara, all these satellites were built by India, but none of them were launched by India. Only starting from Rohini, we have started launching from India. Is it clear? Okay. So next we are going to learn about different systems used by ISRO. So when we learn about different systems, for convenience, I've divided it into three types: legacy systems, operational systems, and future systems. When we say legacy means they are not used actively by ISRO right now. That is, the older systems or the past systems are called as legacy system. Then operational system means it is used by ISRO till date. Future system means the systems that are under research. Take a look at this: legacy, operational, and future systems. The same mind map again will be available in your academic book. Page number 12 in your book, you can write page number 12. Right. First, we will start with legacy systems. You can put the right list. Legacy systems of ISRO. Under legacy systems of ISRO, first one is, see here, the entire launch fleet of India. First, we are starting with SLV-3. Put the right list, SLV-3, basic information about the systems. First line, you can write India's first fully operational launch vehicle. India's first fully operational launch vehicle. Second line, you can write three-staged launch vehicle. SLV-3, it's a three-staged launch vehicle. Three-staged launch vehicle. And then you can write all solid motor. When we say all solid motor, it means all the three stages were powered only by solid fuel. No liquid fuel, no cryogenic fuel. How many stages in SLV-3? 3 stages. All the 3 stages had solid fuel. And this was India's first fully functional launch vehicle. Coming to the payload capacity, you can write the payload capacity was limited to 40 kilogram, and that was also limited to low Earth orbit. 40 kilogram to the LEO or low Earth orbit. And you could see it has no capability to carry things till GTO or geostationary Earth orbit. It was limited only to the low Earth orbit. Next is notable launches or important launch. You can write the Rohini system. Notable launches or important launches, you can write the Rohini system. You're going to follow the same template for all the launch vehicles of ISRO. Important technologies, what's the payload capacity, and what are the important launches. Next one is ASLV. ASLV stands for Augmented Satellite Launch Vehicle. ASLV or Augmented Satellite Launch Vehicle. What's meant by augmentation? Adding capacity is called as augmentation. Augmenting is you are bringing together resources. So SLV is satellite launch vehicle, ASLV is augmented satellite launch vehicle. The primary difference between these two is, look at this and this. Visually, what is the difference that you see here compared to this and this? Something is attached, additional things are attached here. Yes. So this is SLV-3, looks like a single stem here, but this one has 2 additional components here. And you see here, the additional components are releasing, gases here, but this engine is not turned on. So these are called as the strap-on motors, or otherwise called as the boosters. First, you can write, it's a 5-stage launch vehicle. It was a 5-staged launch vehicle. And then you can write all solid fuel. All the 5 stages were powered only by solid fuel. Augmented satellite launch vehicle of India, it had 5 stages and all solid. And also the first launch vehicle of India to use strap-on motors, or otherwise called as boosters, called as strap-on motors or boosters. Noted? Okay. So these strap-on motors, they will give the additional push. For example, the picture that you see here, this is called as the Fat Albert. It's a huge or a bulky plane that belongs to the US Air Force. The biggest challenge in heavily loaded planes is they need a longer runway. In fact, across India, there are only 2 places where you can land or take off exceptionally huge planes. One is the Chhatrapati Shivaji terminus in Mumbai, the other one is the Indira Gandhi terminus in Delhi, because you have 3,000 plus acres and you have longer runways. But all airports cannot host such heavy flights. In such cases, they will take off like this. Take a look at this. Do you see they have attached jets here? Look at the ascending angle, almost vertical. Yes. But this gives a short duration, but a high thrust. By the time this gets over, this is already attained velocity, correct? Now, the remaining engines, they will take care of rest of the journey. This method, which is only handled by the defense agencies, this is called as the JATO. The JATO, that is jet assisted takeoff. They're using the jet to take off. If you use the same JATO on a launch vehicle, you call it a strap-on motors. Is it clear? Jet assisted takeoff is what we use in defense terms. But if the same is used here, these are called as strap-on motors. Why is it called a strap-on? Just like how you tie a belt or a buckle. These are just attached with a belt or sometimes using bolster mechanisms. Once the launch vehicle attains enough velocity, this will be detached. The first thing to get detached would be usually boosters. Is it clear? India started using boosters from which launch vehicle? ASLV. So which means the payload capacity will be higher. You can write the payload capacity. It was increased up to 150 kilogram. What was the earlier payload capacity for SLV? 40. And look at this, 150 kilogram. But again, it was limited to low Earth orbit. It was not able to go till medium Earth orbit or high Earth orbit. It was limited to low Earth orbit. Then notable launches, right in all uppercase, SROS, Stretched Rohini Satellite System. That is, the Rohini system was expanded using additional satellites called as SROS. Stretched Rohini Satellite System. Noted. These two are not active anymore. Why they are not active anymore? Because both SLV3 and ASLV, they had a success rate of 50%, which means if you launch it 10 times, 5 times it will be successful, 5 times it will be a failure. They were not reliable launch vehicles, but the Indian science community learned a lot from these launch vehicles. And that's why we have taken them away from the service, but we honor them by calling them as legacy systems. We learned a lot from them. Coming to the operational systems, you can put the title as operational systems. For the operational systems, First one is PSLV. Called as the Polar Satellite Launch Vehicle, PSLV, or Polar Satellite Launch Vehicle. First line you can write, it's a 4-staged launch vehicle. You could see the alternative colors here, white, maroon, altogether 4 stages. It's a 4-stage launch vehicle. When we are counting the stages, we are not counting the strap-on motors. Usually, strap-on motors are just additional components. They're not treated as stages. Clear? The 4-stage launch vehicle, which alternatively uses solid, liquid, solid, and liquid respectively. That is, first stage is solid fuel, second is liquid, third is again solid, fourth is again liquid. Four-staged launch vehicle. Different stages have different fuels here. Before we go to the next one, any idea why we have alternative layers of solid and liquid? Why don't we put complete solid fuel? Or why don't we put complete liquid fuel? The simple answer is cost. Liquid fuels are costlier. Solid fuels are cheaper. So what you do is, when you take off a launch vehicle, I told about the layers of the atmosphere, no? When you talk about the layers of the atmosphere, the bottom layer is thicker. The top layer is thinner. Initially, when the vehicle takes off, it is in the thickest part of the atmosphere. So it has to expend a lot of fuel, which will lavish a lot of fuel. Since you are lavishing a lot of fuel when you burn this stage, we put solid fuel here. It is economic. You can expend a lot of fuel. Then you put a liquid to gain velocity. Again, you put solid before it crosses the atmosphere. Again, you put liquid when it crosses the atmosphere. So we have alternative layers of solid and liquid in this case. Clear? For solid, it's okay. But for liquid, we need a special engine design. India indigenously designed liquid engines called as Vikas engines. And right? Name of the indigenous engines. Indigenous liquid engines. Vikas engines are the indigenous liquid engines designed by India. Vikas is the indigenous liquid engine designed by India. Any idea on who developed it? Have you heard about Dr. Narayanan, the famous espionage case? He is from Kerala. So Dr. Narayanan and his team in late 1970s and 80s, they designed the Vikas engine. Till now, we are using the same engine, the same design with very little improvisation. Clear? Okay. When you see the term Vikas, you always link it with liquid engines of India. Clear? Can you go to the next one? Coming to the payload capacity. When you include a liquid engine, the payload capacity increases and the distance traveled also increases. And right, for PSLV, the payload capacity to the low Earth orbit and then to the geostationary transfer orbit. To the low Earth orbit, it's around 1750 kilogram. And to the GTO, it is 1425 kilogram. Is it needed to exactly remember the values? No. Remember it as sub 2 tons. That is, PSLV is capable of carrying less than 2 tons, not beyond that. You keep it this way. Noted? Yes. Then important launches or notable launches. The first important launch, Chandrayaan 1, Mangalyaan, Astrosat, or Aditya L1. All familiar programs, correct? That's because PSLV is the most reliable launch vehicle. After writing this, you can write till date. We consider PSLV as workhorse of ISRO. We call PSLV as workhorse, or we can say it is the most reliable launch vehicle. When we say reliable, it is trustworthy. It has very lesser failure rates. That's the reason. Do you know how many failures for PSLV till date? Only 3. And out of 3, if you see here, how many launches here? 60. How many success? 57. How many complete failures? 2, and 1 is a partial failure. When we say partial failure, the failure would have happened because of some other system, maybe the satellite itself or some human error. So that's why we call it as partial failure. So complete failure of PSLV, it's only 2. The success rate of PSLV for 60 launches is more than 95%. And that's why we say PSLV is the most reliable launch vehicle. If India has a program and if the payload is less than 2 ton, the most preferred launch vehicle will always be PSLV, because you could see here it has no cryogenic engines, only solid and liquid, no complexity. We kept the design very simple, which is the main reason for successful rate also. And that's the reason we have never altered PSLV. PSLV, however it is designed, we have kept the same design. Very mild variations based on the boosters will be there, core only or poem model. There are different models, but the main stem, that is these 4 stages, are never altered, mainly for reliability. Is it clear? Can you go to the next? Next is GSLV Mark II. Next is GSLV Mark II. The first line you can write, it's a 3-stage launch vehicle. 3-stage launch vehicle. Out of these three stages, you can write it uses solid, liquid, and cryogenic engine respectively. First stage is solid, second stage is liquid, and third stage is cryogenic. Solid, liquid, and cryogenic. Noted. We are going to learn about cryogenic a bit later. So what you have to understand here is, till now we have not used the term cryogenic. This is the first time we are using it, which means SLV3, ASLV, PSLV, none of these launch vehicle uses cryogenic engine. Only the GSLV series, Geosynchronous Satellite Launch Vehicle series, uses cryogenic engine. Have you understood this? Next, you can write the payload capacity. Payload capacity. If you take the GSLV Mark II, to the low Earth orbit, it's capable of carrying 6,000 kilogram. And to the geostationary transfer orbit, it's capable of carrying 2,500 kilogram, 2.5 ton to the GTO, and 6 ton to the low Earth orbit. Two and a half ton to the GTO and 6 tons to the low Earth orbit. Notable launches, you can write most of the GSAT satellites. When we say GSAT, geosynchronous satellites, or most of the communication satellites of India, they were sent using GSLV Mark II. Understood this? Right. Next, the additional topic is cryogenic upper stage program. Under the same GSLV Mark II, we are going to learn only about the cryogenic stage. Cryogenic upper stage program of India. So to understand the cryogenic upper stage program, let's take I have a glass and it's only gases inside right now. Yes, it is empty and it has gas inside. I'm going to close the glass and I'm going to heat it. When I heat the glass, the air inside also gets heated. What will happen to the gases present inside? It will expand. And how about the molecules present here? Will it move slower or faster? Faster. When you heat, thermal energy increases. When thermal energy increases, the kinetic energy also increases. So heat increases and also the velocity increases. Imagine the other way around. I'm going to cool down. When you cool down, what will happen? The gases will compress. When you were heating, it was expanding. When you're cooling down, it is going to compress. At the same time, the molecules will move slower. And at some point of time, the gas will turn into liquid, what we call as liquefaction temperature of the gases. Have you heard about LPG, liquefied petroleum gas? So petroleum gas can be liquefied at a particular low temperature. Similar to that, you have LNG, liquefied natural gas. Natural gas can be liquefied at a particular temperature. Very similar to that. If you take a cryogenic upper stage, we are going to use hydrogen as fuel and oxygen as oxidizer. That is, when hydrogen and purest form of hydrogen and purest form of oxygen, when they're going to mix with each other, they're hypergolic in nature. They will burn, they will produce a lot of thrust. Hydrogen, is it a solid, liquid, or gas? Gas. Oxygen is gas. But we are going to convert hydrogen into liquid and oxygen into liquid. How this is going to happen is, you have to supercool it. That is, the hydrogen will turn into liquid at negative 253 degrees Celsius, extremely low temperature. You have to cool it so that the gas turns into liquid here. Coming to oxygen, oxygen will turn into liquid at negative 183 degrees Celsius, extremely low temperature. But there is one challenge here. That is, if hydrogen becomes liquid at what temperature? Negative 253. You have to store it at the same temperature. If the temperature increases, again it will turn into gas. So you need negative 253 degrees Celsius during the production, during the transportation, and also during the storage. Producing cryogenic fuel is not easier. Producing cryogenic oxidizer is also not easier. Then why is that India is adopting this particular technology? What could be the reason? Weight reduction, good. And then it is more costlier. Solid, liquid, and cryogenic. Cryogenic is more costlier. But there is one more reason. One is weight reduction. The other thing is efficiency, or the amount of gas that can be derived for every kilogram. But in simple words, energy density is much more higher. So I'm writing here, before you copy the other one, solid, and then you have liquid fuel, and then you have cryogenic fuel. Which will be the costliest one? Cryogenic fuel. Moving from left to right. Moving from left to right, the cost increases. Then moving from left to right, I'm also writing efficiency, or the specific impulse. Specific impulse also increases. There is one more major advantage here. That is, you were telling about storage or weight, correct? Let's take, I have 7 kilogram of hydrogen. Imagine the container size that's needed for storing 7 kilogram of hydrogen. But if I liquefy it, this will turn into 1 liter of liquid hydrogen. That is, in this container, in 1 liter, I can store 7 kilogram, or energy equivalent to 7 kilogram of hydrogen. Let's take, we have a launch vehicle. At tip of the launch vehicle, I'm going to store 1000 liters of liquid hydrogen. When I say 1000 liters, it basically means we are storing 7000 kilogram of gaseous hydrogen. When you want, you'll be able to convert it. And that's the reason, especially for long distance missions and everything, we'll be using cryogenic upper stage. Clear? So I can copy this now. Specific impulse is higher for cryogenic and cost is also higher for cryogenic. Noted? Yes. Now, coming to the engine that we use here for GSLV Mark II, the engine that's used here, it's called as liquid engine. You know that it's called as Vikas engine. For solid engine, we don't have a name specifically, but the cryogenic engine that we use here, it's called as CE 7.5. For GSLV Mark II, you can write. India's first indigenous cryogenic engine is called as CE 7.5. Cryogenic engine 7.5. CE stands for cryogenic engine. 7.5 is the variant. India's first cryogenic engine. Is that clear? Coming to the next one, the next launch vehicle we are going to talk about. But before that, see the GSLV Mark II. How many launches? 16. How many success? 10, 4 complete failures and 2 partial failures, which means it's not having a very impressive launch record, but we learned a lot from these engines. And then we designed something called as GSLV Mark III. So you put the right list. GSLV Mark III. It's known by different names. We also use the term Launch Vehicle Mark III, LVM3 or GSLV Mark III. And in newspapers, in recent times, did you see something called as HRLVM3? That is Human Rated Launch Vehicle Mark III. Everything means the same with minor modification. You have GSLV Mark III for sending satellites. And then for Gaganyaan program, we have modified it so that humans can be accommodated inside. Those are called as Human Rated Launch Vehicle Mark III. You see the term GSLV Mark III, LVM Mark III, or HRLVM Mark III. All of them uses very similar technology. They belong to the same variant, or they belong to the same infrastructure with small changes in the variations or changes in the infrastructure. I will tell you one by one. Okay. First line is, take a look at all the launch vehicles given here. Which one appears to be the tallest one? Mark II. The tallest one is Mark II. Then which one looks well built? Mark III. Yes, because if you see, when we launch GSLV Mark II, it will be around 414 tons. But when you launch this will be around 640 tons. Look at the difference here, at least 200 tons extra compared to GSLV Mark II. You can write 3 important terms here: largest, heaviest, and the most powerful launch vehicle of India. GSLV Mark III is the largest, heaviest, and the most powerful launch vehicle of India. Largest, heaviest, and the most powerful launch vehicle of India. Noted. And next line you can write, it's a 3-staged launch vehicle. 3-staged launch vehicle. When we say 3-stage, the first stage is solid, second stage is liquid, third stage is cryogenic. Same as GSLV Mark II, solid, liquid, and cryogenic. But the only difference here is, I said, boosters will not be counted as a stage, correct? But here, the booster itself is counted as the first stage of all Indian launch vehicles, because look at the size of the booster here. It's almost half the size of PSLV, because the boosters here, they alone carry 200 tons of fuel, which means we cannot treat it as a minor stage. And that's why we have written 3-stage, solid, liquid, and cryogenic. What was the name of India's first cryogenic engine? CE 7.5, but here it uses C20 or C25, which is India's most powerful cryogenic engine. We can write CE20 or C25. It's India's most powerful cryogenic engine. First cryogenic engine is CE7.5. Most powerful cryogenic engine is C25 or CE20. Yes. So which means payload capacity should be higher here. You have more powerful engines. The payload capacity is also higher. You can write, coming to payload capacity, the low Earth orbit and the geostationary transfer orbit. The low Earth orbit, it can carry up to 8,000 kilogram or 8 ton. The geostationary transfer orbit, it can carry up to 4,000 kilogram or 4 tons. 8,000 kilogram and 4,000 kilogram respectively for the LEO and GTO. The most notable launches, we can write Chandrayaan 2 and Chandrayaan 3. Two important launches of GSLV Mark 3, Chandrayaan 2 and Chandrayaan 3. And very important upcoming program, Gaganyaan. This will be discussed later in your class. For now, you remember Gaganyaan or Chandrayaan 2 or Chandrayaan 3 should be associated with GSLV Mark 3. Chandrayaan 1 was launched using PSLV. I will explain why we used PSLV for Chandrayaan 1 and GSLV for Chandrayaan 2 and 3 a bit later. For now, you learn this. Yes? Can you go to the next? Yes. Did we miss any other? Yeah, coming to the success rate. Very interestingly, take a look at this. How many launches? 7 launches. Everything is successful. So it was commercially started only in 2015, and so far 7 launches. All the 7 are successful. In terms of absolute value, you can write GSLV Mark 3 has 100% success rate. The only Indian launch vehicle with 100% success rate is GSLV Mark 3. But most number of successful launches, it is PSLV, and that's why we label that as reliable. Only Indian launch vehicle with 100% success rate. Till now we have learned about cryogenic fuel mostly, correct? But I meant to tell you solid fuel and liquid fuel. There are a lot of solid fuels and liquid fuels that are used across the world. We are going to learn only about the Indian fuels. You can write, whenever you see the term butadiene, take a look at this, HTPB or hydroxyl terminated polybutadiene. We are not going to remember the entire term. Write only this butadiene hyphen series of solid fuels used by India. Whenever you see the term, family of chemicals with the suffix butadiene. Butadiene, series of solid fuels used by India. Then, when you see the term hydrazine, unsymmetrical dimethyl hydrazine or monomethyl hydrazine, all these are liquid fuels used by India. You can write the family of fuels with the suffix hydrazine, generally hydrazine hyphen liquid fuel. Butadiene, solid fuel, hydrazine, liquid fuel. Yes, the remaining you have learned already. See here. For HTPP, we have not given any oxidizer because usually it starts from the ground where atmosphere itself has a lot of air, oxygen-rich environment. Then you have UDMH, unsymmetrical dimethyl hydrazine, which is a fuel. And look at the oxidizer here. Nitrogen tetroxide will provide oxygen. Monomethyl hydrazine, which is fuel. Mixer oxides of nitrogen is oxidizer. Coming to cryogenic, liquid hydrogen is fuel, liquid oxygen is oxidizer. I've given you the same tabular column in page number 12. Page number 12 in your book. They're in page number 12. Yes. Can you go to the next? Okay. And the last one is sounding rockets. Next is sounding rockets. So what's the use of a sounding rocket is, let's say I'm designing a very small system that can be integrated into GSLV or PSLV. Do you know what's the cost for launching PSLV once? It's around 150 crore rupee. And then for GSLV Mark II or Mark III, it goes up to 300 crore rupee. Now, for testing the system that's around 10,000 rupee, I cannot build the entire PSLV. I cannot build the entire GSLV. For that purpose, we have a small sized launch vehicle called as sounding rockets. Sounding rocket itself means research rockets. We will put this system on the sounding rockets and we will test it repeatedly, say 10 or 20 times, we will repeatedly test. And if every parameters are not showing any anomalies, we will directly integrate it into PSLV or GSLV. In simple method, it's a test bed for integrating systems into bigger systems. I can write sounding rockets are research rockets. Sounding rockets are research rockets, which generally serves two purposes. One is for upper atmospheric research. Sometimes we use it for upper atmospheric research. Sounding rockets are research rockets used for upper atmospheric research, or they're used for testing new prototypes and subsystems. New prototypes and subsystems. Is it clear? Whenever you see the term RH followed by a suffix, do you remember RH-75, India's first sounding rocket? Right now we have RH-200, which means RH is Rohini, 200 centimeters the diameter. Then we have RH-300 Mark I. Then you have RH-560 Mark II. These are some sounding rockets of India. So whenever you see the prefix RH, you can assume that it's only for research purpose. We are not sending it for any other mainstream purposes. Is it clear? Yeah, I will finish it. Have you understood this? Yes. So far, we have completed till operational systems. From tomorrow, we will start with future systems. I'll tell you a general outsketch. Every time I finish a class, we'll tell you what are we going to deal in the next class. So tomorrow's class, we will learn about future systems. And followed by that, we will learn about private player participation in the space industry. Do you know that private players can participate now? Yes. We'll learn about that. And we will learn about different satellite systems owned by India. That is, which satellite is used for communication purpose, which satellite is used for Earth observation, which is used for navigation. All these will be discussed. And along with that, Indian systems, which means IRNSS, Gaganyaan program, all other systems will be dealt tomorrow. Is it clear? Yes. Online participants as well as offline, are you comfortable with pace of the class? Is it comfortable? No problem. Okay. Well, see you tomorrow. Thank you.